Okay, lads. So what we call the tension of the rope is T, and that's T and T. So it's one rope. The tension is the same through all the ropes. Is that all right? Now, next thing. What Sarge said earlier was, yeah. Oh, thank you. And what Sarge said earlier was, if you give up 20 centimeters of rope from particle B, this rope will be spread evenly as 10 centimeters aside with A. Hence, for every 20 centimeters B moves, A will only move 10. So therefore, the acceleration of B is twice that of A. Okay? Now, you can say that that's A and that's A over 2, but I don't know why you'd want to introduce a fraction unnecessarily. So for me, sorry. You can say that's A and that's A over 2, but I don't know why you'd want to put in a fraction unnecessarily. So for me, I'm going to go for 2A and A. Is that right with you guys? No questions thus far? Are we good? Alright. Now, so particle A is not sinking into the table, which means that it's fully supported by the reaction force R. Okay? And what can I say about A? 4G going downwards. And what can we say about B? 8G, alright? Now, if you're in a test, which one's the easy marks? B is the easy marks. Now we agree that B is going upwards and A is going to the right. So let's start off with particle B. It's definitely going upwards. So mass times acceleration equals tension going upwards minus its weight going downwards. Is everybody familiar with the system that if you say it's going up, you start off with up minus down, yeah? Up. Alright, so here's what we're going to do. It's 8A, sorry, 8 times, not AA, 8 times 2A.
Just explain again why the AA, the B is 2A and A is just A.
Okay, so just one more time on why B is 2A and the other particle is A. So imagine this, imagine that B goes upwards, okay? And it gives up 20 centimeters of rope. Alright? That 20 centimeters of rope travels up here. Okay? But what happens is it gets shared equally with this pulley, top and bottom. So it'll get shared equally as 10 centimeters either side. And that will only move A across 10 centimeters. So because it's connected by it's connected by the same wire twice, if you get what I'm saying. For every 20 centimeters you give up of one of this rope, it will be shared equally 10 aside on the other pulley system. So hence it will move only half as fast. Okay. Now, and then what do we just have? T minus 8G, yeah? Happy days. Alright, the next one, guys, is we're going to go for B now. Now there's friction in here as well, isn't there? What exactly are we getting friction of? 4/7 of the R value. So what's 4/7 of the R value? 4/7 of 4G, is it? And you said that's 16 over 7G. Yeah, happy enough with that? Alright. Now, we're all agreed that A is moving to the right, so it's MA, but it's going to the right. Now, what's forcing it to go to the right? P value. And what's opposing that force? How many tensions? 2T. And friction? Yeah. And MA is simply 4A, is it? Oh, sorry lads, it tells us what P is. So P is 320, isn't it? completely unnecessary to, you should have said 320 at the beginning. Anyways, here we are. Now, let's look downwards. What letter could we get rid of here? I'm thinking about multiplying this by 2 and then adding it directly underneath. So I'll get through 2a equals 2t minus 16g. I'll get 36a equals, what are we looking at there, lads? Will somebody add 16 over 7 to 16 for me? 128 over 7. Did you get that, did you?
Yeah.
Grand. And then just divide that by 36 and give me the answer.
3.91.
Alright, so we'll go for 3.91 on this. Oh, sorry, not 360, 36. 3.91 ms minus 2. I actually have the marking scheme up here somewhere. Yeah, happy days. Now, the tension in the string. Now, you're probably thinking, why am I so interested in this, alright? So I'm about to do something at the very end. So that's you're going to have to be familiar with something you've never seen before, okay? So, the next thing is tension T. So T equals 16a, 16 times the acceleration plus 8 times gravity, and then T equals 16 times 3.91 plus 8 times 9.2, and what you get for that? Sorry, 8 times 9.8. What you get for that, you? 140.97. Yeah, 140.97 newtons. That's perfect, okay? Now, here comes the curveball for you, okay? So, what I'm going to do here is just going to explain a quick system. So currently, you guys are very used to blocks on surfaces like so. Is that okay? And what happens earlier was we got pulled by a force of 320 newtons, yeah, and there was a reaction force R, and there was our weight of, for argument's sake, just 4g still. Is that okay with you guys? Now, imagine a system, a bit like a clothesline. Imagine you tether a bag over a clothesline. Do you get what I'm saying? So you have like a clothesline, okay? And what you do is you have a little metal ring, okay? So the metal ring tethers a block onto a clothesline. Is that okay? And there's still friction, isn't there? There'll be friction between the metal ring and the clothesline, wouldn't there? And it can still be pulled across, similar to the question we did earlier. Is that alright? Now what way does the reaction force work this time? It still supports it going upwards. It just doesn't do it from underneath. Do you get what I'm saying? It's still tethered to it, and the weight will still go downwards. And if I say there's a friction of a half, what would you say here? Friction of a half?
2g.
Yeah, still just 2g to the left. So, another type of question, as I said, it was news to me, but it could look something like this. Alright? So, imagine instead this system here, okay, and I just take all this out. Okay. Now, imagine it looks something like this instead. And oh, sorry, it's still on. So it's basically tethered, or it's hung from a rod. Okay? Do you understand? It's actually the exact same question.
Yeah.
It's exactly the same deal. R goes upwards, your mu value is 47. You actually get the exact same answer. Is that right, you guys? So if you ever flip something at you like that, that's how you deal with that. Okay? Cool. Any questions about that? We all good? All right.